period of a point charge kept near a ring of charge. There are two things given here. That means you have got a ring, and this ring has a radius r, and the total charge given to the ring is q. And what if you are having from the center, you are at the center, you are keeping a negative charge minus q. If you slightly push this charge to this side or this side through a small distance x, so the charge is here, and you see this x, the distance x that you are pushing through has to be far smaller than the radius. In such case, what happens, this negative charge kept at the center oscillates simple harmonically. So I am just letting it out at the beginning itself. You will see why. Because electric field near a ring of charge, is k q x by r square plus x square whole power 3 by 2. When the x is very small, x square compared to r square is negligible. So this equation becomes k q x by, because x is small, x square, that means x is far less than r, x square plus r square is just r square whole power 3 by 2, which is nothing but r cube. So k cube by r cube into x. So the electric field at any point very close to the center of the ring is k q by r cube into x. That means field is proportional to x. If field is proportional to x, then the force is also supposed to be proportional to x, because we know that electric field is a force on 1 coulomb charge. Here you have kept a charge of minus q coulomb. Then electric force, if you write electric force, from this you know force is equal to charge into electric field. Here you have got a negative charge. Then when you just push this negative charge slightly through this distance x, then it will experience, because the ring is of positive charge, this charge is negative, then this negative charge will experience a pull towards the center again. That pull is equal to QE, because when you push this to this side and the force will act in the opposite direction, this will be minus. That naturally comes because the charge is negative. Then the electric force that is acting on this point charge minus q back towards the center of the ring is equal to minus q times the electric field. But the electric field due to a ring of charges k q x by r cube. Then in such cases, if force is known, then this force is acting on this charge that produces acceleration of the charge toward the center. We know that force is equal to mass into acceleration. Here force acting on the point charge is equal to mass of the point charge into acceleration. Then basically this force has got to be equal to this, or this electric force only is producing this acceleration. Then ma equal to, we will be writing ma is equal to minus q into k q by r cube into x. If you rewrite this in a slightly better way, acceleration is equal to minus k q by m r cube into x. A standard equation for simple harmonic acceleration. A is equal to minus omega square x. Comparing these two equations, the acceleration of a charge kept near a ring is minus k cube by mr cube into x, but acceleration of a simple harmonic oscillation is minus omega square x. In such cases, comparing these two, we will be getting to know that omega square for this point charge kept near a ring is k cube by mr cube. Hence, we will be writing omega square is equal to k q by m r cube, which means omega is equal to root over. So when you take square root, this square disappears, this becomes minus, kqq by mr cube. But we know that omega is equal to 2 pi by time period. 2 pi by time period is equal to root over. Here you know that k is 1 by 4 pi epsilon naught into qq by mr cube. This can further be written as t can be taken here, this whole thing can be brought over here, t equal to, and I'll take one more step here, this is equal to q by 4 pi epsilon naught m r cube. So this way time period is equal to 2 pi into root over 4 pi epsilon naught m r cube by qq. This is the time period of oscillation of a point charge kept near a charged ring.